The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, ladies and gentlemen, and welcome on today's webinar that will be mainly focusing on how to effectively use tools for 2D members. My name is Martin Matuška, and here at SCIA I work as a product development engineer. And together with me also my colleague Vladimír Příbramský is here, who is our product manager, and he will be answering your questions during the presentation. Now, before we get to the actual presentation, please let me mention a few organizational details. We're broadcasting this webinar using GoToWebinar tool, which means that during the presentation your audio will be muted. However, if you want to raise any kind of question, you can do so using the box questions at the bottom of the GoToWebinar panel. And last but not least, this webinar will be recorded and it will be posted at our SCIA YouTube channel. Now, let's have a look at the agenda. What are we going to talk about? I've divided this webinar to 3 separate topics. First, I would like to introduce our new feature called Integration Member. Then we will have a look at averaging strips, and at the end, I'm gonna show how to work with RIPs. So, as a first topic, we can go directly to Integration Member. I've already mentioned that it is a new feature that was actually presented at version 19 and further improved it in our currently released version 19.1. And what can actually provide this tool to you? How can you use it, and why should you use it? Well, it basically can it can integrate internal forces, or not only internal forces, but results in general on a defined area. And later on, you can present such integrated results in the manners of 1D members, meaning that in terms of internal forces, you will receive 7 components of internal forces, and with the deformation, you will get 6 separate components of deformation. Now, first of all, we should somehow have a look on how to define such integration member. For that, I will go directly to the SCIA Engineer environment, and you can see I have here a very simple structure, 2 walls perpendicular to each other, and I would like to integrate their internal forces and see how we are doing here. So for that, I need to first define my integration member. There are actually 2 ways how to do so, or I can find them in 2 separate places in our main tree. Either I can go to the structure service, and here I have a group for 2D members and subgroup for components, and right almost at the bottom you can find integration member. Or you can go to the results, and here we have tools for 2D results, and again here is a command for integration member. Now, what is the benefit of these 2 positions? Well, as you probably know, result service is not always available to you unless you are you have already calculated the structure. The service itself is not present. So if you want to define your integration member during the definition of the model, you can do so from the structure service. So let me call this command, and you see that when I do so, I will receive this definition dialog where I can set my parameters. The name is quite obvious and self-explanatory, but what about the bounding box? Well, that is actually an object that defines the area from which results will be integrated. So we can see that I have 4 options over here. I would assume that most likely in most cases you will use rectangle or square. However, if for any case you will need circle, bounding box, well, you have it here. So for now, I will stay with the rectangle. Now, other parameters I will explain later on. So for now, let's say we are okay with them, and I will confirm this dialog. And now I need to define the longitudinal definition of this integration member. So as you can see, you get directly to the mode where you can switch in between several options. Either I can go with the line, or I can switch to polyline mode, or I can select any kind of curve offered here. For now, I'm going to be okay with the straight line. So I will define first point and the end point and confirm by escape. And now you can see that integration member has been inputted into the structure. And what if I want to see the result of integration? Well, for that I need to go to the beams, because as I mentioned, I will present them in manners of 1D member, so internal forces. Now, very important thing is that if I want to display results on integration member, and it also applies for integration strip, which you might be familiar with, I need to activate this checkbox. Without that, you can see that nothing is displayed. So once activated, I can see that results are integrated, and I can display particular components and see how I'm doing. So let's have a look at other parameters as I promised. So in properties, we can see that bounding box we went through. So now another one is integration relative to position of. Well, this is actually a new development featured in release 19.1. And what is it good for? Well, for that, let me just go slightly to the different direction of this project. So what do I have here? I have the same structure in here. The only difference is how I define the integration member. In first case, over here, I define it at the corner of this structure, while over here I tried to find a center of gravity of such structure, and I inputted it to this position. Now, what's the difference? Well, let's see. So I'm gonna display a normal first. For now, it seems everything is okay, same. And the same applies also for shear forces. However, if we have a look at the bending moment, now it's a different story, because over here, well, there's basically no bending moment. And over here, I have a significant bending moment. So how is that caused? Well, that is actually caused by the fact that over here, the integration is actually executed to the position of this corner, while here I'm almost at the center of gravity. If I would get exactly to the center of gravity, I would get 0. So I slightly failed here. However, just to presentation purposes, I think this is sufficient. So where this bending moment gets from, if I measure the eccentricity over here, I will get something like 0.724, and the normal force over here is approximately 106. So if I go to the calculator and multiply how was it? 0.724 multiplied by 107. I will get approximately the bending moment of this case. So that's how this actually bending moment is generated. And obviously, if I would try to find the center of gravity in every case I want to use integration member, well, that would get easily overwhelming. So for that reason, as I mentioned, in version 19.1, we introduced this option to define where I want to integrate my internal forces to, whether it is definition axis or center of gravity. So if I switch to this option and then I will press F5, you can see that right now I'm getting 0 or almost 0 bending moment. So that's exactly what I want to do. Now, if I switch back to the normal forces, and we can have a look at the other parameter again. This is new in version 19.1. For each integration member, you can directly define number of sections you want to have the results presented on. Before that, you would have to use the general setting in the calculation setup. So right now I can define for each and every integration member separate number of sections. So let's have a look what will happen if I increase the number of sections here to 100. You can see that really 100 section has been generated, and I have a very fine resolution of results. Now I would like to point out one remark here. Be careful with this, because, well, in some edge cases, it may happen then that if the difference in between the size of your mesh element is and the distance between two sections is too high, you may somehow get corrupted results, because right now and you've already noticed it, that we're only doing post-processing calculations. So the results from the general calculation remains, and I'm only presenting them in a different manners. So you should always try to have similar size of mesh elements to the distances between each section on integration member. Now, let's have a look at the rest of the parameters. Well, for selection of members, I will later on switch to the more complex project, so let's skip it for now. And we also have here local coordinate system. Well, this local coordinate system definition was actually taken from the 1D member, so you're probably familiar with it. Pretty straightforward. If I select integration member again and let's say rotate the local coordinate system by 45 degrees, and then again refresh, you can see that automatically it is recalculated to the proper local coordinate system. So easy as that. And then of course layer, I don't think it needs any explanation. So with a simple model, we're done, and we can move on to, as promised, to a more complex structure. So here I have a multi-story building. If we have a look at it, it is actually quite tall, and in terms of the shape, a bit complicated. And of course, I have a core here, and I would like to somehow work with the results on the whole core. How can I do it? Well, obviously I can use integration member for this. So I've already defined my integration member over here. The shape I've set to square, and it has a side of 10 meters. Now, as you can see, not only the core itself is within the integration area, but also some members, in this case, some columns are actually inside the integration area. Well, that could very easily damage my results, or my results wouldn't be correct enough. And for that reason, I would like to get rid of them. And as you expect, for that, we have this selection of members for integration option here with two possible items, all or user-defined. Now, if I switch to user-defined, you can see that new property appears, manual exclude. And if I open it, here I have a complete list of all the members inside, and so I can define my selection of excluded members. Now, in this case, I could easily unselect all the beams, and I know that I would get proper results, but it's not always as easy as that. And so in many cases, this is not sufficient tool, obviously. So there is also plan B, and that is to use this action button, exclude members from integration. If I execute this action button, I'm in a selecting mode, so very easily by using mouse, I can select all the members that will be excluded from the integration. Now, if I confirm by escape, and let's say go back, you can see that these lists, these members are actually still selected. You can also see them inside of this manual exclusion. And now, if I go to the results, beams, internal forces, I need to activate the integration member and strip checkbox. And if I refresh, I should get rid of all the not necessary members to see it properly. So yeah, now I'm just gonna select the integration member, hit F5 to refresh, and I can see that my normal force has been integrated and are displayed over here. Now, you may wonder what happened with the slabs, because in the integration area, I don't only have walls, but I also have all the floors here, or the slabs. Are they integrated or are they not? Well, they're not, because obviously that would not be very, very useful for me. So as long as your ceilings or slabs are perfectly perpendicular to the walls, they're not excluded, not included in the integration, which is handy. Of course, if somehow the slab would be inclined, then it works in a way that each section creates sort of a plane, and every single mesh element that it meets, it integrates from. So in this case, most probably part of the slab would be also taken into account. Few of the mesh elements would be taken into the account during the integration. However, still, it is manageable. I would only have to exclude those members from integration, and still I would be okay. So that's a remark I wanted to point out here. And we can move on to another project I've prepared for this presentation. This time it's a bridge structure, but quite complicated one, because you can see that not only it is curved directionally, it is also curved vertically. So quite complex, but in fact, in reality, very common case. And you may think that it will be very complicated to input integration member on such structure. Well, it's quite the opposite. So if I go to the results and call for integration member, I'm not going to change anything. Maybe this one here, because right now we're focusing on the longitudinal definition. So what I have to do is I need to switch to new arc instead of straight line. And then I need to specify 3 points. So start point, then any intermediate I want, and of course the endpoint, confirm by escape, and voila, my integration member is ready. The only thing I can notice here is that not all the structure or the whole bridge is inside, so I need to modify the offset of bounding box. So the bottom I will increase the offset to 6. Confirm. And now if I select integration member, go to the results, internal forces, selection only current. Now we want to see bending moment. If I display results, oh, I still need to activate this integration member and strip checkbox and F5. Yes, well, as you can see, this is not what I would expect it. Well, obviously it is caused by the fact that the number of sections on integration member is not sufficient. So let me just quickly fix it. F5 to refresh. I still need to select my integration member. And now I'm getting the diagram I would expect, more or less. So this is how to very quickly input integration member on more complex structure with curved geometry. Okay, I can close this project and in terms of the integration member, last project I want to show is again case where integration member can be very helpful. So I have a structure here. It is a kind of a building, not really a real project, but just to present how it could work. And I have a ceiling here that actually has 2 levels. So there's actually a bit of a level change in here. Not enough to have a separate ceiling, just enough to make my calculation nightmare. Because how should I define this? It is sort of a rib. However, our current ribs will not support this use case because one slab is added at the top, the other one at the bottom. But I can use integration member for it. So let's have a look. Again, I will call for integration member. I will define my bounding box as a square, and I will input 2 integration members. Now, if we go to the internal forces and display bending moments, very easily I can get my internal forces on which I can actually design this structural part as a beam and define my reinforcement accordingly. And with this, we got to the end of the first part of this webinar, focusing on the integration member, and we can move on to the next topic. Of course, if you have any question regarding integration member, don't hesitate and use the question box where you can ask your question and my colleague will answer them. Now let me get back to the presentation. Next topic are integration strips. What integration strips are useful for, or when they can be useful? Well, I've tried to demonstrate it on following two pictures. First is something that should simulate the real structure that has volumes, has 3 dimensions. The other one is our model in SCIA Engineer that always reduce the model through 1 dimension. And as you can see, the actual contact here in between slab and, in this case, column actually is done on a single node. Well, this may lead to the state where internal forces and tensions are actually accumulated in one point and at a very small area that can lead to some peaks and in some specific cases also to singularities. And yeah, there's not much to do with singularities if you want to design let's say reinforcement for them. So how can you handle it? Well, for this we have averaging strips. So I will switch back to SCIA Engineer environment, and yeah, let me just quickly close these projects. We will not need them anymore. Also the first one. Yep. And let's open this again very simple model where I will explain how to input averaging strips, and I will try to also explain some aspects to it that may seem a bit confusing. So here I have a very simple structure. You've seen it on the slide. And if I have a look at results, I will have a look at the bending moment as expected. I have a peak over here, quite huge one. Well, if I would want to work with it, it could easily get very, very complicated. And also I can see that it's accumulated really near the node. So this is a perfect example of example where I should use averaging strip. And how should I do that? Well, in the result service, there are again tools for 2D members, and I have averaging strip here. So let's have a look at parameters over here. First of all, there is a type. Well, we have 2 types, strip and point. Well, it is quite obvious, but where to use which? Well, of course, if there is a intersection of slab and 1D member, such as column, most likely I'm going to use averaging strip, the point one, while when there is an intersection in between 2 walls or 2 slabs, and there is a risk of peaks, well, then I'm going to use strip. So let me get back to SCIA Engineer environment. I'm gonna input strip. No, I'm gonna input point integration, averaging strip, and here I need to define width and length. How should I define these sizes? Well, they should somehow reflect the actual size of my elements, structural elements. So in general, the dimensions should be around 2 times of the thickness of your slab, maximum 3 times. It shouldn't be more. So now I'm going to confirm it and input it to my slab. And now if we have a look at the internal forces, now again, there is a checkbox for averaging peaks. Without it activated, well, you can see nothing changes. Once I activate it, you can see that actually the results are recalculated. I have average values over here. That's what I wanted. Now, how these averages are actually calculated? Well, we have two directions, of course. So how can I read these results? Well, for that, or to better understand it, I'm gonna turn on results on section and I'm gonna refresh. So you can see that in one direction I have very nice peak over here, while in the other direction the value seems to be constant. Well, that's actually exactly how it's calculated. If we have a look again at normal results, in each section on the averaging strip, I get approximately average value. So that's how it's done. And if I have a look at the other direction, so it's a Y bending moment, I get the same. In one direction, exact peak, and in the other direction, approximately average value. So this is actually how the averaging is done. Now, what's the difference between those two directions? So let's have a look again at the definition. I can see that I have two options here, or several options here for directions. I have a longitudinal, perpendicular, both, or none. Well, none obviously will not do much, but if I switch only to longitudinal and confirm, so first let's have a look again at the X direction. Here nothing is changed. Again, I'm getting average values. But if I have at the other direction, Y direction, now nothing is actually averaged. So I'm getting the peak again. And there's a difference on how the directions are actually stored or gathered for each type. So as I mentioned, we have two types of averaging strips: point and line. And let me switch again to different part of this project to demonstrate it. To demonstrate it a bit better. So in this case, I have a structure. Well, three rows that there are exact, and on each there is a averaging strip defined. Now, in first case, I have a point strip, while the other two are actually strips. And strips are defined by 2 points. And that is very important because now let me refresh the results. And we want the other moment. For some reason, at the first case and the last case, I get average results, while here I don't. In case of a point strip, the longitudinal direction is always estimated based on the main slab, or and based on its x-axis. So in this case, it is in this direction. But with a strip, it actually depends on how you define it. In this case, it was actually defined from the bottom to the top, while over here it was defined from the left to the right. So in this case, my longitudinal direction is this one, and that's why it's actually integrated. While in this case, it's from the top to the from the bottom to the top. So, and since the direction is longitudinal, nothing is actually averaged. And another thing I would like to point out that may be sometimes confusing for you, why it doesn't work as you would expect, is, and let me again select a proper part of this project, is that in fact your structure needs to be perfectly in plane. So I have 4 walls right now. Here obviously I can see it's not really in one plane, so I'm going to refresh the results, and I can see that over here it is actually averaged on both sides. So even though the master slab is this one, as long as the whole wall is in one plane, then I still get proper results. Now, in this case, I can directly see that yeah, it's not in one plane, so I only get averaging on 1/2. And what's happening over here? Well, now if we have the value of coordinates of nodes here, y coordinate is 0, while on the other hand, on the other side, there's 1 extra millimeter. So this tiny little change can actually cause that the integration or the averaging is not executed as you would expect it. Now, what I can do here is I have 2 options. Either I will fix my structure, so I will move those nodes, or I can define my averaging strip on both slabs, and either way I will get proper results. Now, this would be it for the averaging strips, and we can directly go to the last topic, and those are rips. Now, again, I will show on a simple structure how to define rips, and also we will have a look at how the redistribution of internal forces works in this case, and then I will also show you a few tips how to handle a normal force that you wouldn't expect. So again, I'm going to switch to SCIA Engineer environment, and I will open first project. Now here we have a very simple structure. It's a slab supported along its sides, and I would like to input a rip. For that I need to go to the structure service, 1D members, and over here I have a command for rips. And again, I have special definition dialog where I can set my parameters. So obviously very important one is a cross-section, where I can either select any cross-section from my library, or I can actually create new one. But for now I'm okay with this 500 by 500 cross-section. And again, the rest of the parameters we will talk about them once the rip is defined. So I need to define 2 points, and the rip is there. Now let's have a look at the rest of the parameters. We have options for alignment, so either bottom, center, or the top. I assume bottom alignment will be most common case, so I will stick with that. Then we have a shape of rip. Now there are several options here. Again, T symmetric. Well, again, I would in case of rips in the middle of the slab, most likely a very common case. if the rib is at the edge of slab, then you can select slab right, slab left, or you can have also non-symmetrical slab. And there are also several options how to define effective width. Now, either I can define it directly in millimeters or by number of thicknesses, or use the default option. This option actually doesn't do nothing else that it looks in the solver settings to this value. So if you change your global setting and you want to use it for all ribs, then you can use the default settings. Now, we also have two options for definition of effective width. And why is that? Well, most probably we'll get to this later on. So for now, I will leave this open. And this way, I can run calculation. And once I get my results, I can display results on the rib. Again, a very important thing. If I want to display results on rib, I need to actually activate this checkbox, because without that, of course, I'm getting I'm getting results, but those results are actually only from the rib part. So I've defined some effective width, so I have my T section. However, until I activate this this checkbox, I only get part of the results from the rib, which obviously I don't want to. I want to design my reinforcement on the whole T section. And how this redistribution actually works, let's have a look at second project. Now, over there I have this very simple structure. It's a ribbed slab with a length of 1 meter, with this section. For the simplicity sakes, the center of gravity of the whole cross section is in fact right where the slab meets the rib. And so let's have a look at it. And if we have a look at the results, but this time on 2D results, you can see that again also here I have option for the ribs. So if I display, for instance, bending moment mx, without it activated, I have here my bending moment, while when I activate it, it disappears. Well, it doesn't really disappear. It is only redistributed to the rib. So I actually, my internal forces on the rib itself are increased by what has been actually integrated here. And the same applies for the normal force. So without the rib being activated, I get these results. When it's on, again, 0. And how this redistribution is actually executed, let me switch to my presentation. So I have my components. I have a bending moment in the slab. This is actually integrated value from the whole section. I have also normal force. Again, this is average value on the whole section. Then I have my bending moment on the beam and bending normal force on the beam. So altogether, I get these components: normal force, in the rib and normal force in the slab, and 2 bending moments. Now I need to establish equilibrium, so normal forces added together should determine my internal force in terms of normal force, and then this equilibrium for moments, which means that I need to add a moment of a rib and slab, and then also normal force acting on a inner lever, in both cases in a beam or in a rib and in a slab, and altogether it gives a bending moment 8.98. So if I go back to my model and have a look at the normal force on selected sections, you can see that yeah, that's what we have here, and the same applies for my bending moment. But the problem here is that if I compare this kind of structure to very simplified model where I only have one beam, but the cross section is actually the same. And if I have a look at the normal force, you can see that over here, and that I would expect, I have 0, because this kind of beams is only loaded by its own weight, while over here I have some kind of a normal force. Where it gets from? Well, it gets from this equilibrium. So because of how I set my effective width, the normal force is not in equilibrium. Now, how I can handle it? Well, there are 2 ways. One very complicated one, and this one I will try to show you on the last project over here. I can try. So over here I have again a ripped slab, as you can see, and I have on one side rib with a constant width, and if I have a look at results and normal force over here, current, yeah, there's normal force present. So what I can do is, and I've done it here, I've divided this beam on the other side and defined for each section different width. So if we have a look at the results, now as you can see, yeah, it is almost 0. So I got what I wanted. However, to do this in real life, yeah, it can get overwhelming. So yeah, you're not actually want to work this way. So because we wanted to find some solution, we went directly to the concrete service, and we've added an extra option over here. If you go to concrete settings and internal forces, there is option to neglect in normal force in rib. Well, this I would say is not the best way how to name it, because you're not actually neglecting it completely. If you have a look at this remark, you can see that you're neglecting it, but you are also adding extra moments. So you're actually redistributing this normal force into the additional bending moment. And that way you will get basically the design of reinforcement just as if it would have zero normal force, but with an increased bending moment. So that's a much more efficient way how to handle this phenomena. Now, by that, I got to the end of my presentation. So thank you very much for joining us in here. And of course, I will still leave this webinar open for a while. So if you have any additional question, just go ahead and ask us, and we will answer it to you. So thank you again for your attendance, and hopefully see you in our upcoming webinars.